Okay, so let's talk about polar bonds and electronegativity. I've drawn here the Lewis structure for water, which I think I did on the last video. And we did the electronegativity difference was, let me get those numbers. So for oxygen, it's 3.5 and hydrogen is 2.1. So 3.5 minus 2.1 equals 1.4, which makes it polar covalent. And if I were to draw this using molecular geometries, we would come over here and we'd see that we have 4 electron groups, but only 2 bonds. So the molecular geometry is bent. The electronic geometry is tetrahedral. So how is that going to look? Well, we start with the central atom, and I put my 2 lone pairs on that. And then I have a bond angle here of about 109. That doesn't look exactly right, but it's close enough for today. And we know that this was oxygen and this was hydrogen. So this end, the oxygen end, is somewhat negative. And this is just a lower Greek letter delta. And that means somewhat or partial. And so there's a partial negative charge in this region of oxygen, and there's a partial positive region near the hydrogen, and it's true for both bonds. And so we see that if I were to draw a dipole moment, and a dipole moment just means we have an arrow and it goes from the positive region to the negative region. And so the positive end is the hydrogens, the negative end is the oxygen. So we would have an arrow pointing towards the oxygen on both sides here. And that means there would be a net dipole. And that net dipole would have the oxygen as negative and the hydrogen as positive. So if I were to do another example, let's do carbon dioxide. And I've done this one in class, so you should have it in your notes. And if I put the dots in, and you should be able to recognize now that this molecular geometry is linear. And going back and looking at oxygen is still 3.5 and carbon is 2.5. So 3.5 minus 2.5 equals 1.0. So this will be polar, or the bonds are polar. But is the molecule polar? Well, and this was oxygen minus carbon. And so the negative region will be the higher electronegativity, which is here. And so this is going to be somewhat positive, and this is going to be somewhat negative. And this is going to be somewhat negative and somewhat positive again. So my arrow should point in these directions. But in this case, we have an electronegativity difference of 1.0 in this direction and 1.0 in the exact opposite direction. So what that means then is that these dipoles will cancel. And if they cancel, there's no net dipole. And so this molecule is non-polar. So if the dipoles do not cancel, if they're at an angle to each other, then there would be a dipole, and we will have a net dipole for this molecule that would be facing the oxygen. And in this case, there's no net dipole because these two are facing in opposite directions and will cancel out. Canceling dipoles, you would have to have all groups the same. And that would be on the central atom. Second, you would have to have them cancel. You would have to look at their geometry. And it would cancel if it was something like tetrahedral. If it was linear. If it was trigonal planar. And you would also have no lone pairs on the central atom. So I hope that helps with this one. Let me know if you need anything else.